Our new topic is work and energy. So first of all, the idea of work. Work will cause a change of energy to occur, so it will be transferred from one type to another or transformed from one type of energy to another. So in the example here, the chemical energy in the rocket fuel will be transferred to kinetic energy, which is the moving energy of the rocket, and that's called work. So whenever work is done, you get a transfer of energy. So that's the link between work and energy. Work done is energy transferred. That's going to be done in joules, so that's the units, capital J, a shortcut. So 500 joules of work means that 500 joules of energy is transferred. So in terms of the amount of work done, it depends on a few factors. The first one would be the amount of force that's needed to be used to actually move an object. So the weightlifter here is doing a larger force on the right and therefore should be doing more work. The fireman here that's doing the most work there is the one that's climbed the highest on the ladder, because it also, not just force, it's based on the distance the object's moved. So the distance moved by the object in this case is the fireman up the tall ladder is bigger than the fireman on the shorter ladder. Does the application of force to an object always result in work? If the object doesn't move, then no useful work is done. So just bear that in mind. Even though you're exerting some energy there, the definition in physics is that useful work is when a force causes an object to actually physically move. If it doesn't move, then no real work has been done. And the formula for this then is work equals force times by distance moved. So force is in newtons. So force will be in newtons. Distance moved is measured in meters, and the work done is measured in joules. So here's some examples you can follow here. You could actually try putting a weight onto this here and try lifting it up a metre. So the amount of the work done is 30,000 joules, because if you check it, it's 30,000 newtons of force times by 1 metre, so the working is something like that. Force times distance, 30,000 times by 1. Okay. If you try just the 20 kilonewton weight here, try lifting it 3 metres, what we've got there is 60,000 joules, because again it's force times distance, 20,000 newtons times by 3 metres, so you get 60,000 joules. Now if you start to link this up with energy, there's lots of different types of energy, but physicists tend to depend on gravitational potential energy and kinetic energy, which is the moving one. So if you look at this rock here, at this particular photo, it looks like there's not much involved in potential energy here. But if you look at it from this point of view, you can see that the rock is above the ground level, so it does have gravitational potential energy. If you could release that, that would convert to another type of energy. It would roll down the hill. And don't forget that rolling or moving is actually kinetic energy. And one of the factors that affects that is how fast you're going, how slow you're going, and your mass that you've got as well. So there's a formula for that. If we have a look at this skater here, you can see it's going up and down. So what's happening here is I've got a skate park where there's no friction, so you'll find they don't lose any energy overall. It doesn't get converted by friction to heat. So looking at that, it's going through there. When they're in different positions here, above the ground at this height, you've got a certain amount of gravitational potential energy because you're above the ground, and they've got zero kinetic energy because they've stopped moving and turned around. What happens as they fall down is that gravitational potential energy will turn to kinetic, and it will start to speed up. And just here, at that blue dot at the bottom, you'll find the kinetic energy is at a maximum and the gravitational potential energy is at a minimum. And they convert between the two here, so the total energy stays the same. So if you look at this graph here, you can find out here that the kinetic energy in the green there is very, very high. There's virtually no potential energy, and the total's in yellow. If you watch this motion, then you'll see the total stays the same, but it moves between one type of energy, kinetic, to the other, potential. Okay. If we get this right down on the ground here, on ground level, you should see just about there that it will convert all to kinetic as it hits that blue dot. Okay. And then we should just go through one frame at a time. There it is there. The kinetic energy is at a maximum there, potential energy is the minimum. And then it should actually change again. And just about at the top here, the kinetic energy will stop, so no kinetic energy at all, potential energy to the maximum. And the total is always staying the same. So it's just converting from one type to the other. So just be aware of those types of energy. In each case, work is being done. Work is being done by gravity to pull this down here and actually accelerate it from kinetic to potential, potential to kinetic, and vice versa here.